9. Okay, for attendance today, the password is Subhanallah. Okay, the password for today is Subhanallah. So you can write down in the attendance. Give you a few minutes to fill it in the attendance first. Finish? Okay. So inshallah we'll continue from last time. What did we discuss last time?
Electron, proton, and electron hole.
Okay, so electron hole pairs. So Islam, why did you come late? Waalaikumsalam. Why are you late?
Was opening my computer.
I cannot hear you.
I was opening my computer.
Can anybody hear him or understand what he says?
I think he said he was opening his computer, right?
So you're supposed to open your computer 10 minutes before the class or 30 minutes before class, okay? So this time I still allow, next time I will not admit if you are anybody come late. So 8:30, everybody should wait in the waiting room already. Okay. Otherwise, as I mentioned, you can watch the first video. This is the rule of my class. So if you don't like the rules, you're not happy, I already told you, so no need to put in the SFS because I already told in the beginning. If anybody not happy with my rule, you are not forced to stay in this class. Anybody, I'm not saying to anybody in particular, but in general, if you don't like the rules, you cannot follow the rules, you are not happy even with the rules, you are not forced to be here. So you can choose many other electives, even from another program or department. Okay. Because in the end, why I keep on repeating this, because in the end I see somebody still commenting at the end, so it makes me furious that in the first place why the student join my class and in the end complain. So if you are not happy, then you don't have to stay, right? So okay, so that's, I want to make that clear, right? So okay, so let's go back to, anybody knows what is the electron hole pair?
Electron and hole. It works with pair because positive charge, negative charge. It's carrier. Holes and.
Why do they call it electron hole pair? Why is
Because it must move together, just like positive, negative. Just like,
not accurate. So anybody else wants to try?
Just like lock and hole for the key. Key and hole for the key. Just like that.
For the key. So before that, let me address people who come late. My Sarah, why did you come late? My Sarah, why did you come late?
My laptop has problem.
Okay,
Last night, so So I just
Okay, this is the second
sing
time.
it.
Second time already, my Sarah. So next time, half an hour. Make sure your laptop before the class. Make sure your laptop is okay. As I mentioned to everybody before this, siapa lambat saya tak bagi masuk dah. So please settle whatever problem like 30 minutes before. If you say, Madam, I tried to solve this 30 minutes before the class but cannot, then I will accept. But if you only open like 5 minutes before the class and you have problem, then it's your fault. Okay. Kalau if it's a face-to-face class, I will say okay, I will just lock the door. Tak bagi masuk lah. There's another one. So because of those who come late, you disrupting the class for everybody else. Hassan, are you there?
Yes, madam. Assalamualaikum.
Salam. Why did you come late?
Ma'am, I got up a bit late. That's why. It's 6:30 in Bangladesh. So after Fajr, I just fell asleep. So that's why I got a bit late. Sorry. Inshallah, it won't happen the next time.
Okay, inshallah it won't happen, and if it happens, I will not allow you to come to the class already. Okay.
Okay, no problem. Inshallah. Yes.
Alright, so let's continue. Okay, electron hole pair. Siapa tadi nak jawab? Who wants to answer that? Yeah.
I have a long answer though.
Okay, try your long answer.
Okay, so what I found out was that in materials there are valence band and conduction band, and the valence band is filled with electrons while the conduction band is empty at ground level. So when sufficient energy is provided to the electrons, they get excited and jumps to the conduction band. And when the electron jumps from valence to conduction band, it leaves a hole in the valence band. The hole in the valence band and the electron in the conduction band are attracted to each other by electrostatic force, and that forms a pair. That's what I found out.
Okay, that's good. That's a good answer. So it's called electron hole pair because whenever you have any excitation of electron from the valence band to the conduction band, it will produce a pair. So whenever you have this excitation from the electron from the valence band to the conduction band, it will not only produce electron but also hold in the same time. So that's why it's called a pair. Okay, so that is if it's between band to band. Later on we'll talk about what is band, what's valence band, conduction band. Okay, good. Right, so we done that, finish, understand. So what's next that I ask you to do to find out? Faris,
Material, madam.
apa? Rahimi?
Material, madam.
Material, semiconductor. What is it? Is that so? Ke?
Yes, what is semiconductor material and its type?
Okay, what is a semiconductor material? Fadli. Fadli? Yeah. Menyesal masuk kelas ni. Mungkinlah.
Semiconductor material. There are many different type of semiconductor material. Each of them have slightly different properties and different applications in various form.
Brother, Abang Fadli. Nanti budak Tiap-tiap 5 tanya Abang Fadli, apa tu semiconductor material? Abang Fadli, what does semiconductor material means? Form 5 student ask you. Okay, can you please answer again?
The first material is germanium.
I'm not asking the examples of semiconductor. I was what is semiconductor material? Okay, who wants to help Fadli?
Hello, madam. Yes.
Okay, Simon.
So semiconductor material from the name itself is semi-material. So it is partially insulator and partially conductor. So the beauty of semiconductor material is that we can control the material to become more conductor or more insulator. So semiconductor material, uh, it can be done if we can control the process. We can control to be more conductor or insulator by the process doping. I think that's the answer. Maybe.
Alright, panjang sikit lah the answer. So from the name semi conductor. So conductor, you know what's a conductor, right? Semi is partially conducting. So semiconductor is a kind of material that has a properties between a conductor and an insulator. Okay, so previously you learn about there's a conductor. What are examples of conductor, Aiman? Bukan Elmi. What? Give me examples of a conductor.
Example of conductor, copper wire.
Okay, copper, aluminium, right? So those are conductor. So an example of insulator, Faris? Faris. Plastic, okay. Plastic, wood, bricks, they are all insulator. So in between these two, there's a type of material that Allah has created where it has a property between a conductor and insulator. Conductor means what? Conductor means it's easily current can easily flow inside it, right? Insulator, what does insulator means? Insulator means that current cannot flow inside a insulator. So semiconductor is a special material where it has a characteristic between conductor and insulator, and macam Aiman was saying, the beauty, Hana is the beauty. So the beauty of it is I like the word beauty. So the beauty of it is when it has a characteristic between a conductor and an insulator, the beauty of it, we can control it to be like a conductor, or we can design it to be more like an insulator. Okay, so as an engineer, we like things that we can control. So as an engineer, do you like things that you cannot control? No. Everything that we do, we want to make sure that it's within our specification. We can control everything. So we know how to control it. So for semiconductor, for conductor, for example, that's a property, you cannot change it anymore until a little bit, maybe you alloy or something. But semiconductor, you can change with one piece of material. With one piece of material, you can change it from from conductor to insulator, and that is the magic basically. So thanks to this semiconductor material, then comes a lot of electronics circuit integrated chips, because of the properties that we can manipulate, we can change. And to change the semiconductor properties, we dope it. Okay, that is my next question. What is doping, Islam?
Again, what is what?
What is doping?
Doping.
Yeah, doping. Have you all had breakfast? You can go and get. Let's eat in the class. I'm also eating just a plain bread lah. Tak sempat I didn't manage to cook. So Islam. Ismail is your father's name?
Father, this is my family name.
Huh?
My family name is my.
Oh, your family name. Okay, Islam. Did you go and did you do a little? Did you watch my first video?
Yeah.
Yeah, so I asked one of it to find out what is doping.
For semiconductors doping?
Yeah.
Dope to generate either a surplus or deficiency in balance electrons.
I cannot hear you. I cannot understand you, brother. You need to speak with your hands not on your mouth. So So this is extra from semiconductor class. When you go for interview or when you talk to others, some people they like to talk like this. Exactly. I want to say that today I want to teach about the semiconductor material. Can you hear me properly? No, right? So sometimes it's a habit. Make sure that when you talk, you don't put something across your. Sometimes you are thinking like this. So don't, when you talk to other people, don't put your hand in front of your mouth, because people cannot understand, hear you properly. So Islam is googling it. So never mind Islam. So next time when I give a homework, try to understand first before. And there are a lot of videos on this. This basic information before we go to the real semiconductor device course. So let's hear from Rahimi. What is doping?
Doping just like modifying the element for semiconductor.
What is doping? If I'm not happy, I will ask the question 100 times. So you need to improvise the answer.
Doping is the intentional introduction of impurity into an intrinsic semiconductor for purpose.
Why?
Because intrinsic is just like a pure material. True ya? Or not?
Ya, saya tak tanya intrinsic tu apa. I'm asking you, you say, so you say doping is a process of what?
Intentional introduction of impurity into intrinsic semiconductor.
So why we put these intentional impurities?
Because we want to modify it.
Why you want to modify it?
For certain purpose.
Ayah, your answer very big lah. Memang, of course, there's a purpose. You don't dope it for like for nothing. For, of course, with a purpose, but what purpose? So you know, your answer must be
to modify their structure property.
Okay, Elmi, do you agree with him or no? So
I agree that by doping we change the semiconductor structure property, but I think the purpose is to ease the electrons and holes to move, to make it better conductor-ish.
Ahmad, what is doping?
From my understanding, Assalamualaikum, can you hear me?
Yes.
It's like, so basically when you have like a pure element like germanium, for example, and semiconductor, basically you want to alter the properties to change the activity.
What is doping?
Madam, to increase the number of electrons or numbers of holes.
Okay, good. Repeat again. What is doping, Rahimi?
To increase electron or hole concentration.
It's a process. That's very important. I keep on. It's a process. So, okay, one thing, brothers and sisters, you will hate this subject because why? This subject is very specific and accurate. So you cannot miss certain words. For doping, it's a process. Dopant is the material that we dope the impurity. So if you skip the word process, then we don't know what is doping. Doping, is it a material? Is it what? So doping is the process of putting dopant, or another words, dopant, impurities is the same thing. Okay, don't get confused. Sometimes the reason why they call it the dopant impurities because we add dopant to a pure semiconductor. Okay, so that's why they call anything extra, they call it impurities. And it's the same as dopants. Okay, so but impurities can mean other things, but in the doping process you add impurities, meaning the dopant inside the semiconductor material. But in other words, in another situation, impurities can mean something else. It means that you add dirt, you know, to the you can have dirt inside the semiconductor. So but in the doping process, the impurities that Rahimi was saying is the dopant. So if you go and read many books, I know when you do this you read, I know I was hoping that you be reading a lot of books, and you go to many websites and YouTube channel, you will see that when they explain about these terms, they are explaining in different words. Okay, so that is the other thing that makes semiconductor sometimes confusing to students. This book say dopant, this book say impurities, this book say something else, while it just means the same thing, but the wording they choose is different. Okay, so that's why things, if you are not clear, then you ask in the class, what does it mean? Does it mean the same? Sometimes it means the same, sometimes it means slightly different. But the concept of doping is basically to add, it's a process that you add impurities, you add dopant inside a pure semiconductor to make it either n-type or p-type. To make it, why do you want to make it n-type or p-type? Because you want to have extra, n-type means you have extra what? Kamalia?
N-type extra electron.
Okay, p-type?
P-type with extra hole.
Good. So n-type and p-type. So this doping process is to create a semiconductor material which is n-type or p-type. So n-type means majority electron, p-type means majority hole. Okay, brothers and sisters, this is the basic, and do not confuse, because why I keep on emphasizing this, but later on we'll go like more complicated and you got confused with the n-type and p-type, then that's it lah, crumble. Because you start confused and you don't remember which one which, is very difficult for the thought process later on. Okay, so this is very basic. I'm going very basic so that our basic is strong, so that when we understand the higher level of the concept, it's easy for you to understand. So if you don't understand, you should ask now the basics. Okay, any question up to here? No. Alright, so we have electron, we have hole, we have doping, we have dopant. What else question I asked you to find out?
Band gap.
Band gap. Okay, Ahmad, what is a band gap?
Band gap is the gap between the conduction band and the valence band. Basically, so you have metals, the band gap is like almost minimum, or there's no band gap. Semiconductor, there's a bit of band gap, and insulator, there is a big band gap. The band gap is the amount of energy or excitations from the electrons to move from one band to the other. Maybe the last part I might kind of got it wrong, but
okay, good. But how do you get the band gap? Where does the band gap theory comes from? In your O level or in your Form 5, do you learn about band gap? What do you know about atoms? Atoms in a material. Do you learn about the band gap? Do you understand my question?
Yeah, I mean like the structure of the atom, right?
So where does the band gap coming from?
How the materials are inside the atom are distance between them.
Repeat.
Electrostatic.
Terima kasih tapi bukan.
Madam, is it from the lattice constant? The lattice, what is it? Lattice structure.
Lattice.
Lattice, dia punya susunan atom.
So how does the susunan atom come up, then brings out the band gap?
Wait.
Wait, okay. Everybody wait, okay.
I think that from the principle, madam, is it
Principle?
Pauli exclusion principle? No.
Okay, good. Explain.
Okay, so Pauli exclusion principle is that there is a lattice. Lattice constant is the what is meant by lattice. Wait. So lattice constant is a distance between each atom. So the lattice itself is the arrangement of atom in regular manner. So we
We are talking about you're talking about the Pauli exclusion. Why you go for the lattice?
oh yeah.
Ayah. Awak ni dah suruh kita wait tu salah kat tu.
So based on Pauli exclusion principle, it split the conduction band and valence band become become energy band diagram.
Do you understand or not the concept?
I'm trying to understand, but not really.
Yeah. So ask me any question.
Madam.
Yeah.
Madam tanya yang macam type SPM.
Yes, during SPM, yes.
Dia macam metal tu ada.
You need to speak English, brother. Ahmad cannot understand. Ismail also. So we don't want people to like get depressed or cry in this class.
Energy for metal electrovalent. Metal and metal, and then another one non-metal and non-metal. What we call, I don't remember.
Okay, thank you for your attempt again, Rahimi. So so in your like form 5 or your O level, basically what you learn is in the semiconductor, not semiconductor, any material, basically you have atoms, right? Like this. That is in an array, betul tak? Right? So this is the nucleus. I'm drawing the nucleus. Then let's have the blue. So then from each of the atom you have the orbit, right? Yes or no? This is what you learn in your form 5.
Yes.
And then if I'm going to draw this, too many to draw. So can you imagine in one piece, like a very small piece, 1 cm or 1 cm or 1 millimeter by 1 millimeter, there are millions of this atom, right? Inside one very small tiny piece, there are millions of the atom comprising the material. Okay, so you have millions of this atom. Okay, this atom ni million, I cannot draw them. So what happens? And there are millions, but they're in a very tight space. So now I'm going exaggerating a bit. So it's going. So you can see this. Now you will see that this orbit here is interacting with another orbit, right? Can you see? So now it's interacting. Okay. So when this happens, exclusion principle that Aiman was saying, the Pauli exclusion principle, he found he do some mathematics, and that's why mathematics is important. That's why you have to, in engineering, you have to make sure you pass and you score your mathematics, because mathematics are important to come up with theories. So Pauli exclusion principle found out that from theoretical that each of these each of these orbit, they cannot, when they like hit each other or meet each other, they will not you cannot have what's the word apa perkataan dia tu yang Pauli exclusion principle says, the exact word, let me find out. I want to use the word that they use. Aiman, do you know what's the word they use? Two or more identical electrons cannot occupy the same quantum state within a quantum system simultaneously. This is the word that if you read Pauli exclusion principle, they will explain that. But but if I'm going to translate that to the way that you understand, it means that for each of the orbit over here, you cannot have the same electron in one orbit or one quantum state. Okay, so what happens is, because of this principle, what happens is, okay, I will draw this again. So now, but I will draw only one rule. This is like 3 rules. I will draw one rule here. So I will draw 3 only atom. So what happens is, so this is from this brothers and sisters. Yeah, there's a brother who just became my. Okay, let's be merciful and at this time, but next time I will not allow anymore. Okay. So this apa nama ni, where I was saying this from the top view. So these are from the top view. So now I'm going to draw from the side view of the atom. Okay, so the side view of the atom, it will look like this. Apa nama ni? Macam mana tu? Macam mana? Something like that. Oh, my drawing is really bad. You can go and watch videos on Pauli exclusion principle. Basically, from the side view, you will have this orbit coming from the nucleus. So what happens is, because of this Pauli exclusion principle, then this orbit will apa nama ni? They will form a band. It will form a band. What does it mean? Basically, this so we can view now. We can view the whole material here, whether it's semiconductor, any kind of material. So because of this Pauli exclusion principle, we can view as, in the end, this orbit over here, this whole orbit will, in the end, because it will separated between 2 types of band. Okay, so the band will be. So when you say a band, ni macam ni sebenarnya. It's like a band like this. Okay. So this is when you this is when you see individual atoms. So also here I'm drawing, you can see 3 individual atoms. But as a whole of the material, where we don't draw, this is like millions of atoms already. When they interact with each other, this orbit, we can manifest, or we can portray them with the energy band diagram. So basically you have 2 bands, and this is the valence band, and the top is the conduction band. And when Warwick was saying, so this is the band gap. My G is not. Okay, this is the band gap. So what is exactly inside this valence band and conduction band? Okay, in these 2 valence band and conduction band, there are multiple, we'll say that, energy level states. These are the words that you need to familiarize yourself. So energy level state. So means that this, can you see here? Every line here that I draw, the blue line here, is the energy level state. So Pauli exclusion principle say it will interact, and therefore it will separate between the 2 bands. And in each band here, you have many of these energy level states, and there will be a gap between, and we call this the band gap. So after this, I will go to what is the definition of energy band gap. Okay, so Okay, now up to here, any question? Hello? Hello? Is there any question?
Madam, when you say each of they have multiple energy level states, what does that mean? So every like electron has a different energy level state, or?
Okay, so do you understand what energy level state means?
No.
So that's the first question you should ask, no?
Okay. What is an energy level state?
Okay, it's a how to say, it's a okay, this is when semiconductor becomes something that you need to imagine. Okay, one thing about semiconductor physics is it's not like mechanical. Anything mechanical you can see, you know, it's moving. You can see it's like you can see it's actually moving, and you will understand it through that. But in semiconductor, because it's too small, and nobody has ever seen this energy level state. But it's a theory that we need to imagine that there's this level state that will hold electron or hold. It will hold HOLD. It will hold either electron or holes. So to simplify things for you, okay, in a material, whenever you're going to find an electron or a hole, okay, whenever an electron or hole need to exist in a material, it has to be inside this energy level state. It cannot be hanging anywhere. So it need to be in that like macam I don't know, like it's like a place where the electron hole need to be. Okay, so in this so if you can see in the valence band and the conduction band here, so it means that if you look in the band gap over here, there's no energy level. It means that theoretically the electron hole cannot be inside the band gap, but because there's no energy level state. Energy, sometimes they call it energy level state, sometimes they call it energy state, sometimes they call energy level. Okay, right, this is the same thing, right? So so for any electron hole, because as a semiconductor, you know, as an engineer in semiconductor, electron hole are the key of everything, because it controls the flow of current. Okay, so therefore electron holes are very important to us. So we need to know where the electron holes are. So the electron holes can only be on this energy state. So for example, if I draw, I can draw electron over here, I can draw electron over here, I can draw a hole over here, I can draw so but I cannot have hole in the middle of the band gap, cannot. So energy level is where, so whenever you see an electron or hole, there must be energy level in this state. Okay, so if it's not there, it's not possible to be there. And if the electron hole are there, it means that there must be energy level over there. Okay, boleh?
Madam.
Yes.
When electron and holes move from valence band to conduction, how do they move? Because the energy band gap is in the middle. Because
okay.
of the energy level states or energy line, how do they move from valence band to conduction band? As they can't be.
Yeah, we will talk about that later. Okay. Right. So any more question? I will explain that later.
Madam.
Yeah.
You said that the energy level state are the state where electron and hole to stay, right? So if the electron and hole doesn't have energy level, so does it mean it is a free carrier?
Okay, so kita tak masuk situ lagi. We're still in the kindergarten level, not yet. Yeah, no, we are in the apa nama ni? So you can imagine we're in the third year, 3 years old. Now we're going to the 4 years old now. So when I say, okay, that's the next question I will ask. So this carrier here, this electron hole, are they free carriers or are they bound carriers? Apa benda pula free carriers? Okay, when I say carriers every time in the class, carriers means, what does carriers means? What does carriers mean?
Electrons and holes.
Yes, so carriers is the element that brings that flows, that gives current. So there are two carriers only inside a semiconductor, which is electron and hole. So when I say free carriers, it means that it can be either electron or hole, or it can be both. Okay, so it's not specific. If I say electron, then it's just electron or hole. So now my question is, this over here in the diagram over here, is it free carriers or no? Free or bound? What's the difference between free and bound carriers?
Free, it mobile carrier. They freely move. Bound is immobile carrier, so it doesn't move.
Okay, good. So now tell me this. Let me label it to make your life easier. Say, let's label this green. I hope anybody colorblind here? Normally the brothers are colorblind. You better mengaku You better admit that you're colorblind. Anybody colorblind here? No? Statistically, brothers are higher chances of colorblind.
I am colorblind.
Who are you?
Am I? Tell me.
Elmi, you're colorblind. So can you see the different colors here, or
Yes.
still get? Okay. So A, B, C, D. Okay. Tell me which one are the free carriers and which one are the bound carriers from this diagram, A, B, C, D.
All bound.
Okay, Rahmi answer all bound. Everybody has to answer this.
A and C is free carrier.
Apa? Yang mana?
A and C free carrier. B is bound carrier.
A and C, B and C, free carrier yang mana?
A and C free carrier.
Okay, so my Sarah is saying A and C free carrier, B and D bound.
Bound, I think B only. I don't know.
Oh, interesting. Okay, B only. Banyak fatwa and mazahib over here. Okay, next.
B and C bound. A and D free.
B and, again repeat.
B and C bound. A and D free carrier.
Okay, who's answering that? Siapa jawab tadi?
Aiman.
Okay, Aiman. Okay, next.
A and D are the free carriers and B and C are the bound carriers.
Okay, next. So your answer is like Aiman. Next.
A dengan C conduction, A dengan C free, B dengan D bound.
Okay, siapa tu? Who's that? Ikram. Tapi nama
Fadli.
dah, kalau nak panggil nama Ikram tulislah kat situ. Ikram, susah saya nak ni. So your name is Ikram or Fadli? Or both?
Kedua.
Okay. Alright, next.
B and C are free. A and D are bound.
A and D are bound. Okay, opposite of Aiman and
right.
Huh? Apa?
Opposite, sorry. A and C, B and C are bound. A and D are free. Sorry, silap.
Alamak, boleh macam mana ni silap dia. Okay, alright, next. Sama juga dengan tadi. Okay, next. Who's have an answer?
Free carrier A and C.
A and C free carrier bound.
Bound.
B and D bound. Alright, macam-macam jawapan. Okay, next. Who? Everybody answered? Who has an answer?
B and D free carrier. A
Huh?
and C is bound.
B and D free.
A and C is bound. Yeah, B and D is free.
B and D is free. A and C is bound. That's right. Okay, next. Who hasn't answered?
My answer is
E and D free.
Yes, Almi first.
My answer is same with Fadil. A and C are free.
Okay. And bound?
B and D.
Okay. So next.
A and B free, C and D bound.
A and B free.
Yeah.
C and D bound. Okay, next. Macam-macam. Okay, next. Who hasn't answered?
A and C free.
A and C free.
B and D bound.
B and D bound. Okay, next.
And D bound. A and C.
Brother, don't put your hand on near your mouth. We cannot hear you. Bring your mic close.
Yeah, B and D bound. A and C.
Can you speak louder, brother, please?
A and C free. B and D bound.
Okay, finish everybody. Alright, listen carefully, brothers and sisters. This is a very important concept that you will be using throughout this course. So, the correct answer is the answer of Aiman. I think the brother, can't remember the name, from Bangladesh, one brother, and then Hana. So that's the right answer. Okay. Okay. Whenever we do this, okay, right? Remember now this photo over here, and then when it's interacting in the side view, it becomes this, and then it becomes energy band diagram. So when this happens, right? What is free carriers? Free carriers means the electron or the hole can move freely. How is it possible to move freely? Okay, that's a question that we need to ask. Okay. To give that, I will give you a concept. Because semiconductor is like physics are like the concept is like kadang-kadang tu is a bit difficult to understand. So that's why I will give you a concept where I try to give a metaphor so that you will understand easier. Otherwise, it's difficult to understand the concept. So can you imagine in a room? You can imagine a room. This the concept that my supervisor, Professor John, told me, right? And in the class, he said, if we are all in a room, okay, in a classroom, and whereby all can you imagine a full packed? So there's no way, meaning every inch are filled with people. Can we move or no? Cannot. But there are a lot of people, right? Yes, right? So it means that there can be a space where there are a lot of carriers, but it cannot move. The reason why it cannot move is because there's no space for it to move. Okay, so if I give you another analogy, the same room, not the same room, another room, whereby you have a lot of people, but you have empty spaces, right? So when you have empty spaces, then can you move or no?
Yes.
Yes. How do you move? Somebody will go to the empty space, then another person will go there, then will go. That's how you move, right? So similar like this electron holes. Okay, in this band, in the valence band, you have both conduction band and valence band have like energy level state. You just remember energy level state is just like where the electron holes need to stay. Okay, so but the difference is in the valence band, there are lots of electrons, but there are lots of electrons, but there are no empty state. Okay, in valence band there are lots of electrons, but there's no empty state, therefore there's no way the electron can move. But in valence band there are lots of electrons, like the room full of people, but there's no empty state. So the electron, although they are here, many of them, but they cannot move. Contrary, in the conduction band, that's why the concept of electron hole is always the opposite. In the conduction band, there are again many of energy level state, but whether the energy level states, the word is occupied. If you go and read, they will say occupy. The word occupy. So in the valence band, all the energy level states here are being occupied by electrons. So there's no empty state. Or maybe I need to write down the name is empty state. So empty state is important so that the carriers can go there and then move. If there's no empty state, the carriers cannot move. So in the valence band, there are a lot full of electron, but there's no empty state, so the electron cannot move. In the conduction band, it's the opposite. You have a lot of holes, full of holes. There's no empty state for the hole. Okay, now the empty state for electron and hole. So okay, I'm trying to. If you don't understand, tell me. So in the conduction band, you have a lot of hole, but there's no empty state for it to go. So it means it cannot move. So however, in the valence band, okay, let's go back to the valence band. In the valence band, since the valence band are full with electron, there are not many holes. Okay, but there are not many holes in the valence band, but there is. So if no, maybe we should start at 0 Kelvin. Okay, let's go for 0 Kelvin because I tak faham nanti. 0 Kelvin where nothing moves. Okay, and nothing moves including the electron hole. At 0 Kelvin, what you can find, you can only find electrons inside the valence band, and then you can find holes in the conduction band. You don't find so at 0 Kelvin, all of the electron will be in the valence band, all of the holes will be in the conduction band. But as we increase the temperature few Kelvin, this is the question that the brother was asking, then how do you get carriers, how do you get holes over here, how do you get electron over here? Because at 0 Kelvin, when everything doesn't move, all the electrons are in the valence band, and all of the holes are in the conduction band, and nothing can move because it's full. Okay, full. But as we increase the temperature, what happens is, okay, the electron here, so I take one electron in the conduction band, it will gain, okay, so use this word that I use, you will gain enough energy to be excited to the conduction band. So the word is gain energy. So the brother is asking, how is it possible there's nothing in the band gap here, that in the end you can have electron to go over there? Because the electron or the carriers gain energy. So here in this particular case, the electron gain energy. How much energy? How much energy? The question, how much energy? The minimum energy for it to become a free carrier. In order for this electron to become a free electron over here, it needs to overcome a minimum energy of the band gap. So the energy from the temperature that we give to the electron should be minimum of this band gap, so that it can go over there. Okay, so yes,
valence band just like donor.
No, donor is doping donor is when you add impurities. Okay, that's a good question. So this is, I'm talking about, maybe I didn't make it clear, thank you for that. This is our intrinsic semiconductor. I'm talking about intrinsic semiconductor. What is intrinsic semiconductor? Anybody?
Pure.
Pure. What does pure means?
Pure don't have dope.
So no doping.
Impurities.
Huh?
No impurities, right?
No impurity. Can you give me example of intrinsic semiconductor?
Germanium, silicon,
Germanium, silicon, what else?
arsenic.
Huh?
Arsenic, I think it's called.
Arsenic is not a semiconductor.
Gallium arsenide.
Gallium arsenide, what else?
Silicon carbide.
Silicon carbide, what else?
Gallium.
Huh?
Germanium.
Aluminium. Aluminium is not a semiconductor. Huh?
Germanium.
Aluminium is not, as far as I know. What else? Indium gallium nitride. Gallium nitride tu pun tak sebut Aiman. So okay, right. So all this is intrinsic semiconductor. Because normally students get confused. I see always this student, I don't know why students get confused between they think they're confused between intrinsic semiconductor and extrinsic semiconductor, and they confuse between another word that we have in semiconductor is elemental and compound. So so do you know the difference between all this? You learn this in your first year electronics. Do you know the difference? Tell me what's the difference.
Elemental is a single atom, so it silicon and germanium in this case. And compound is the multi-atom. So it is gallium arsenide, silicon carbide, indium gallium nitride, and gallium nitride.
Okay. Okay, yes. So these are two separate categories. So don't confuse between two. Intrinsic semiconductor is a pure semiconductor where there's no impurity. And intrinsic semiconductor can be either elemental or compound. Intrinsic semiconductor can be either elemental or compound. That's why if you see here, both you have elemental semiconductor and compound semiconductor, but it's still intrinsic because it means that it is pure. There's no impurity to make the semiconductor. What is extrinsic semiconductor? What is extrinsic semiconductor?
Extrinsic semiconductor.
Yes, it's what? Rahimi?
It has added the other substance or the other impurity.
Yeah, so extrinsic semiconductor means it's been doped. Okay, so it can be, so extrinsic semiconductor can be this whole thing but doped. So doped with another material, phosphorus or boron. Okay, so don't confuse everybody. Make sure you understand. Any question here before we proceed? No?
No question.
Okay, so we go back. So now the energy band diagram I'm drawing and I'm talking about here is the intrinsic semiconductor where it's pure. There's no impurities. Okay, we're talking about pure semiconductor. It can be either silicon, germanium, gallium arsenide, indium gallium nitride, indium gallium phosphide. Okay, so these are intrinsic semiconductor. So going back, so this electron, in order for it to be free, so all the electrons in the valence band are bound. All electrons in the valence band are bound. Why? Because there's no empty state. So they're always filled with electron. So therefore, in order for it to be free, in order for it to move, it has to go to the conduction band. And how does it go to the conduction band? Is by this electron gaining enough energy to be excited to the conduction band, and the minimum energy that it has to get is the band gap energy. Okay, so that's for electrons. How about hole? Hole is always the opposite in the conduction band. So now I will draw the hole. So in the conduction band, there are a lot of holes, as I mentioned. So this is no longer at 0 Kelvin. So no longer 0 Kelvin. So at a higher than 0 Kelvin, it means that the carrier can gain energy from the temperature, from the heating. Heating gives you energy, right? Heat energy. So from the temperature, if the temperature is beyond 0 Kelvin, there is some heat energy. And this hole, which are a lot in the conduction band, are full with holes. Okay, it's full with holes. So therefore, in order for it to be free, this hole, for it to be free, need to move, it has to go to the valence band. And how does it go to the valence band? It have to gain our energy, because we say gain because it's the energy in the opposite. Tapi the concept easy to understand is the whole will also gain energy of the same amount in order to go over here to be free. Okay, so the concept of electron holes, the electron holes are both carriers, but it will move in the opposite direction. Okay, electron will go over here, hole will be going over here. Even so whenever when the hole are over here, it can freely move. When the hole are already here, it can freely move everywhere inside this valence band. So when electrons over here in the conduction band, it can move freely inside the conduction band. So our aim is for us to conduct electricity, we need to have these free carriers we need this to have these carriers in the right place. So it means that we want the hole to be in the valence band, and we want the electrons to be in the conduction band for it to move. Any question up to here?
Madam, I have a question.
Yes, Ahmad first.
Right. So considering the size and the mass of the hole, right? The hole. So when we give energy to the valence band, the conduction band, the movement of the electron is obviously logically is going to be faster than the movement of the hole to the valence band. Am I right?
Yes, but there's a but. Okay, go on.
Does it happen in real time? Like obviously us, we cannot visualize it, but in their world, is it instant? Like for example, the electrons move quickly from the valence band to the conduction band when they're given enough energy. Obviously, they require less energy compared to the hole. Am I correct?
No. Here the same energy, because it needs to overcome this band gap. Both needs this minimum energy. So both need, in order for it to to be excited to another band, we call it band to band excitement. Both of the electron holes need to gain the same amount of energy. But when you say about whether the holes are heavier compared to the electron, in terms of this generation of the electron hole pair, normally because the time is very fast, we assume it's negligible. There is, of course, the whole will be slightly slower, but that is not significant for us to there is there is an impact. Yes, it will be slightly slower. Therefore, slightly slower in excitation and slightly slower inside movement, but it will still create this electron hole pair.
So they will both happen simultaneously at the same time?
Yes, but slightly slower.
Yeah, okay, got it. So the electrons are faster than the holes, but then they both happen at the same time, right?
Yes, it has to happen at the same time. So this is when you have this every time an electron being excited over here, there will be always a hole will be excited over here. That's why we call it electron hole pair. Every time, I repeat, this electron being excited from the valence band to the conduction band, there will be in the same time a hole being excited from the conduction band to the valence band. That's why when in your first year in electronics, you learn, you just memorize at that time, Ni, the intrinsic carrier concentration, electron equals to hole. You still remember this? So the number of I cannot remember anymore first year. Yeah. So the intrinsic carrier concentration. So this is intrinsic semiconductor. So in intrinsic semiconductor, the number of free, when we talk about electron hole, when we talk about intrinsic carrier concentration here, Allah, hilang dah pula. Ni, it means the free carrier. So, okay, brothers, now I know I've talked about free carrier, bound carrier, but later on, as we go along, we will only talk about the free carriers. Who cares about the bound carrier? Nobody cares. Because the bound carrier doesn't do anything. It doesn't contribute to anything to the current. So we don't care about the bound carrier. We only care about the free carriers. That's why when you your first year, when they talk about the intrinsic carrier concentration, what it means is the free carriers. So in an intrinsic carrier concentration, the number of electrons equals to the number of holes. Why? For every electron that being excited over here, there will be an equal of hole being excited to the opposite direction. Okay. So that's why intrinsic carrier concentration is always the same numbers of electron holes, free electron holes. But extrinsic will be different. We'll talk after this. Okay, any question? Any further question? Just now, siapa nak tanya? No question?
Ma'am, does it only happen when we increase the temperature? I mean,
what does happen? What happens? Which one?
The movement of electron and hole.
Okay, this excitement. So be careful when you say movement in semiconductor. Movement is a bit general. So if you answer movement in the exam, you will not get full mark. You get 50% maybe. So this is you need to be very. You need to choose the right word. For example, I always say this excited. I don't say move. Okay, move. Why? Move is within the band. You move. Within the band, you move. Across the band, you being excited. Okay, right. So why? Because when this is terminology in semiconductor. So when you say the carrier moves, instantly I will understand the carrier moves within the band. Okay. So in your answer in your exam, make sure you choose the right word. Okay. So you say, so your question is, this excitement of carriers from band to band, does it happen only with increasing temperature? Was that your question? The answer is, let Aiman, you answer this. You answer this question.
Again, madam.
Alamak, you didn't hear ke?
Does it mean that the electron and holes gain energy to become excited, to become free?
Brother, you ask the question again. Make sure Aiman understand. Listen, everybody, to the question carefully.
Okay.
I repeated the question many times, Aiman. Okay, go on, brother.
I asked that if this excited situation only occurs when we increase the temperature.
Yes, it is. It only occurs when there is temperature, because temperature is considered as, what we call that, temperature considered as the energy of the surrounding energy. So
okay, stop there. Maisara, do you agree with Aiman or no?
I agree, but I can add more. It's not only temperature. It can be voltage supply, or water supply, temperature,
Water
and
supply will excite electron from valence band to conduction band. How? You tell me the physics.
it supplies voltage. I don't know. I read it on textbook.
Are you sure you're reading it correctly?
Maybe I took it wrong.
Okay. Saya baru nak excited. You say it's not the only way, but then the answer was wrong. Okay. Okay, to answer the reason why I asked the two FIP, because they should know, now they don't know, so I will tell everybody. So for the purpose of this, for the purpose of your for fourth year, maybe you should know, but generally in this class we're talking about mostly on the energy. They will any process, okay, to answer your question, brother, it means that any process that will make this electron gain energy, then this will excite the electron to the other band. So any process that will give you energy. So one process is this electron can gain from the heating of the temperature, heating energy or heat energy from the environment. No, that's not the only way that you can what do you call it, give energy to this electron. One is you can give energy, you can give the energy to the electron through this heat. The other way, you will learn later on. I don't know whether you will learn or later on or no. You will not learn that because you learn electroluminescence. This, since you asked. Photoluminescence. So Ahmad, I think your father previously worked on PL, photoluminescence. So photoluminescence means that you will get light coming out from giving energy to the electron to gain energy, and then it will fall down as another form of energy. Okay, how to make it simple? Okay, let me. So this okay. Normally we draw like this conduction band, valence band. We don't draw the band, the square. We just draw like this, and then so this electron, what you can do, you can shine light. Photo means photoluminescence means here the source of the energy given to this one, the electron, is from light. So heat is a form of energy. Light also can also be is also a form of energy. So you have any light with a certain wavelength and energy, you shine the semiconductor. You shine a semiconductor with a specific light. With this light, so this incoming light, which have an energy greater than the energy of the band gap. So you know, the energy of the light, so it's a EL, energy of the light greater than energy of the band gap. So, and when this light hits this electron over here, this electron will gain the energy, and it will go to the it will go to what they call it, the conduction band. And what happens is this electron can go down again. I haven't gone to this yet. So the electron go up, it can also go down. I will explain. And this process, we call this process excitation, right, just now. And this process, we call this recombination. I will go through this after this, recombination. But I just want to tell you, so it means that to answer the brother's question, you can get energy from the heating. You can also get energy from light coming, shining on your device. So it doesn't have to be heat. You shine a light which has a bigger energy than the band gap. So this electron here will gain energy and go being excited. Okay, that's two answers. Number one, the heating. Number two is the light. Another, which I was hoping, you know, the teacher always has high hope to the students, to Aiman and Maisara. I was hoping they will answer. Okay, not only that, the other thing that can you know, the other thing that can be the energy that can be exciting the exciting the electron is
electricity voltage.
Apa?
Electrochemistry.
Voltage. I mean.
Voltage is wrong. Voltage.
So,
Huh?
electrochemistry, same. Wrong.
Wrong, Rahimi. Wrong. I don't know what you mean. Electrochemistry is another different thing. Cannot. This we are talking about this within the band. Okay. So number 1 is not electrochemistry. Number 3 is radiation. Mai sarang Aiman. So how does it work? Radiation. This is my field. Okay, brothers and sisters. This is what I do. My research. How many years? 10 years. I've been my life with semiconductor device. This is my expertise. And plus of the expertise on semiconductor, my expertise also on radiation. So what happens is with radiation similarly, so you have the conduction band, you have the valence band, and then you have the electron. So whenever radiation hit, proton, electron, gamma, X-ray, okay, so all this radiation have energy. So when it can hit the electron, and this will be excited. And this is how a photodetector works. Later on, we'll talk about photodetector when we talk about PN junction. So the basic concept is this excitation can come from various means, as long as it can impart energy to the carriers inside the band. Okay, brother? Who asked me that question? Okay. Any more question before we proceed? Or we cannot. We only have 2 minutes left. Any more question? So this only basic. We die like this. I don't know. We are going very slow because there are many concepts. Still, we haven't gone into devices yet. Even material pun tak habis. Yes.
If we here we are only talking about when we increase temperature or when we give energy. If we decrease temperature, freeze it, does it happen like this, or it's reverse? I mean, does it have an impact?
Okay, good question. I want you to think about it. Answer to me next class. Okay, brother?
Okay, ma'am.
All of you think of the question, answer me next class. So there are things like a question like this which I like a question like this, that because that from the information that I give you, you should be able to think of the answer, so we can discuss whether what you're thinking, you're on the right track of thinking or no. Okay, so remind me, brother, next class for the first thing in the class for us to answer that question. Okay, any other question? You don't want to ask any more questions because you have to answer it yourself. You should ask questions if you don't understand. This is the fundamental part. If you don't understand, you will be in trouble later. So we talk about now today, you know about excitation. We haven't talked about recombination yet. Just excitation. So you know the free carriers, where the free carrier should be. Electron, in order to be free, it has to be in conduction band. Hole, in order for it to be free, it has to be in the valence band. Okay, so there must be excitation. Excitation can come from many places. So finally, once the electrons are once the electrons are here, once the electrons are already in the conduction band, when the electrons already here, it can move. And hole, when it's already here, it can move. So, however, I want you to read about how the electron then next we will discuss about how the electron hole moves. Is it moving in a one direction, or is it all direction, and what is current? Okay, what is current next? So basically we'll cover that in the next class, inshallah. So that's why very important for you not to miss the class, and that's why very important for you to come early, as I will not allow you to come late and you will suffer for not understanding. Not my fault for not allowing you. Okay, I think that's all for today. Let's end the class. Can we have a brother to recite a dua, please? Okay, brother, go on.
اللهم أعطنا فهم النبيين. Sorry, 1 second.
Okay.
يا حنان يا منان يا بديع السماوات والأرض يا ذا الجلال والإكرام، اللهم آتنا فهم النبيين وحفظ المرسلين المقربين، اللهم افتح علينا أبواب رحمتك وانشر علينا خزائن علمك برحمتك يا أرحم الراحمين.
آمين.
صلى الله على سيدنا محمد وعلى آله وصحبه أجمعين. الحمد لله رب العالمين.
Alhamdulillah Rabbil Alamin. Alright, thank you very much, brother. Let's end with Tasbih Kifarah and Surah Al-Asr. Subhanakallahumma wa bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilaik. Bismillahirrahmanirrahim. Wal 'asr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawassaw bil haqq wa tawassaw bis sabr. Okay, see you next class. Okay, there's no class next week, right? There's holiday. Oh, therefore I will give you homework. So don't.
Next Monday or Wednesday?
Wednesday.
Sorry, Tuesday or Wednesday?
Tuesday.
Thursday, Tuesday. Okay.
No, Tuesday. So there's no class. I should give you homework. Do you want homework or you want class? Actually, we can do class still. So I give you a list of for you to read, or you want to have a class. You choose.
You can give us something to prepare, like a topic to read about or to do research about, so we can be ready.
Yeah, I already gave, but
I don't mind having class as well. I'm cool. I'm fine with anything.
So okay. So Ahmad said fine. The rest of you, I will give you a list to read and make sure you understand. So because you already missed a few class, I don't know. And then I either assume you understand, I'll go forward. Password for attendance was subhanallah. Okay. The rest of you want me to give you homework, like a list, like a page of things for you to read?
I'm okay having class.
I would prefer a class.
The rest, I want everybody to.
I prefer class, madam.
Okay, like
Class as well.
rest of you.
I prefer class.
Class, madam.
Fadli wants holiday, yeah, Fadli?
Class. Already 7 votes. Khalas. We think we are gonna have class.
Okay, so you need to pay me extra for working during the during the holiday. So you need to make a lot of doa for me. Okay, so inshallah we'll have a class, but let's not have 8:30. Let's have it later. Okay, boleh? So we can have a class around 10. Okay, 10 on Tuesday. Alright, and this is consensus. If you don't want to come, it's fine. You don't have to come. You can watch the recording, but as I mentioned, you'll be in trouble. You don't understand. Alright, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, madam.
Thank you, madam.
Thank you, madam.